N-spherical functors.
Well, thank you very much, and I would like to thank the organizers for inviting me to this conference. The talk is called N-spherical functors. So N-spherical stands not for N-sphere, but for some kind of N-fold generalization of the sphere. So this is joint work in progress with David Kapranov and Vadik Shekh. So I first recall the usual concept of spherical functors, which turned out to be so important in many areas related to mirror symmetry. Usual. So we are dealing in the most general formulation, we are dealing with a functor between two triangulated categories, F. So more precisely, they should have some enhancement that we call pre-triangulated, some DG enhancement. The exact functor, and we suppose that I have a right adjoint. Right at F with one star on the right. And as usual here, as well as later, there is a little subtlety as what we understand by right adjoint. So do we understand that home from f of x to y and home from x to f star of y, is it isomorphism or quasi-isomorphism? So let me gloss over this a little. There are ways of making this more precise, but in the talk I will not dwell on this too much. So we have the unit and the co-unit of the adjunction. We have epsilon from identity of the category D to F star composed with F. And we have co-unit, it will be from F composed F star to identity of E. And since we assume that there is a pre-triangulated enhancement, we form the cones of those as new functors. We can have cone of epsilon, call it T sub D, and cone of C equals T D. Sorry, T E. Oops. Yes. T E. So this is a functor from D to D. This is a functor from E to E. So and the F is called spherical. Again, there are different sort of sets of conditions which end up to be equivalent, but somehow let me focus on the most important of them. If those functors are equivalences of categories. So F spherical means T D. It's not completely precise. There are some other conditions, but let me put it like this: are equivalences. Now I want to discuss, before going further, I want to discuss an alternative definition, which is due to Sasha Kuznetsov. And it involves not only the right adjoint, but the left adjoint at the same time. So, suppose there exists a left adjoint. And there is F with a star on the left. Then we can do, again, a version of those things, but they're kind of more interesting. I can write F right adjoint, direct sum F left adjoint, going to the composition. F right adjoint composed with F, composed with F left adjoint. And this from E to E. And call it epsilon 2. Or I can do C2, is similar, but this product would be in the opposite way. I write F left adjoint composed with F compose with right adjoint, and again goes to F. Left adjoint plus F right adjoint from D to D. Then F is spherical if one of them is equivalence. So for instance, on the level of D, and say TD is equivalence, and epsilon 2 is an isomorphism of functors. Like I said.
Codes of those normalisms, those E to E and D to D, are the codes of those roots?
No. I'm saying that the cones, there are two things.
What's the direct sum?
The direct sum of functors is a functor which takes
And the morphism
is given by the components. Yes. Yes. So like, what is this? It's a direct sum of two functors. It has an object. Object says the direct sum of value of the first functor plus the value of the second functor.
How does it go to E?
So it's sorry, E to D. Oh, yeah. I'm there. Yeah. From E to D and from D to E. Yes.
Yeah, it was like,
Yes. Apologize. And from D to E. Yes. From D to E. So then F is spherical. If a TD is an equivalence, and epsilon 2 a quasi-isomorphism, which means that the cone of epsilon 2 is 0. In fact, again, there are different subsets of conditions. One can say that what Kuznetsov originally said, that both of them are quasi-isomorphisms of functors, so the cones of them are 0. So what I want to do, I want to continue this pattern. So, and this looks like a beginning of a pattern, and let me call this pattern complexes of higher adjoints. So suppose that there is not only left adjoint and right adjoint, but suppose we have a second adjoint, which means adjoint to adjoint. We already have it here because this one is the second adjoint to this. But suppose we sort of have all of them. And as many as we need as we go. Suppose F has F second adjoint, which is adjoint to adjoint. That's third adjoint. I know it's the F3, and this would be F2. And the other one will be F minus 1, and so on. As needed. So then we can write something like this, but longer. So, right. Suppose I have the adjoint number P, and compose with adjoint number P minus 1, P plus 1. Compose of the adjoint number Q. So suppose P less or equal than Q. Then, so like what's happening here? Like how this morphism goes. We contract either this to identity or contract this to identity. So we can continue. So here there are several ways of contracting. We can have this pair, this pair, this pair, and get some smaller compositions. So many contractions.
So I'm sorry, what are these again? They are iterated adjoints?
Yes, suppose we have an adjoint to an adjoint.
Okay.
And suppose this other one has another adjoint. So in general, in the triangulated category, if there is a set functor, then it gives you the second adjoint from original functor. So suppose we have all of them as needed.
Okay.
So there are many contractions of pairs. There are many further contractions. So we contract each time when we have still left a consecutive domino. So how should I say it? Yeah. And out of this, by putting plus minus signs, we get a complex of functors. So putting plus minus signs, get a complex of functors. So like here we have a complex of functors of length 2. And this is a complex of functors of length 2. So when we take common, it's like the total object of a complex. So here, once we have a complex, we can form the total object. But let me introduce some notation that we call C, and here I write PQ dot of F. So this goes out of co-units. Or we can similarly sort of reverse everything and put units. So the summons, the combinatorial labels here will be the same, but arrows will go in the opposite direction. So I write C with this arrow, so it means that things decrease. Or I can write C PQ with this arrow will be out of units, and the complexity will increase. So out of units. So it would end up in F. Actually, so out of co-units, then the products, well, the order of products inversed, reversed, order of composition inversed, reversed composition. So it will end with FQ composed with FQ minus 1 composed with FQ. So contractions. Contracted compositions. So let me write a simplest one. Simplest one beyond this and this. For example, I can write so let me write for the case of zero, between 0 and 3.
But are there some examples which motivate the question? I mean, some.
Yes, I will explain examples. Yes, explain example. But the identity goes to F3 composed with F2 plus F3 composed with F plus F1 composed with F, which is F star. And then it will, so there are 3 arrows here. So there is the unit, there is the unit, and there is nothing here. It is 0. Yes. And it goes into F3 composed with F2 composed with F1 composed with F. So again. So whenever we can sort of insert, we insert. Otherwise, it is 0. Or the other one, so maybe the next one corresponding to 0 and 4. Right. So C 0, 4. It would be like this: F plus F second adjoint plus F fourth adjoint. Again, a complex will be of length 3 terms. If I recall correctly, it would be F4 composed with F3 composed with F2 would be plus F4 F1 composed with F plus F4 composed with F3 composed with F plus F2 composed with F1 composed with F, and this will go to the full composition, F4, F3, F2, F star is F1. So what we have here is a series of such complexes, and they're labeled by certain combinatorial set of poset of, let's call them domino constructions. Like this, let's call it poset A EQ of domino contractions. So formed by subsets I inside the interval PQ, which is simply the set of integers between P and Q, P plus 1, Q, obtained by subsequent deletions of dominoes. Of I plus 1. So then the structure of this poset depends on the parity. If Q minus P is odd, then there is a minimal element here, which is the empty set, the empty product. There's always the maximal element, which is the full thing. And if P minus Q is even, then there are several minimal elements. So if Q minus P is odd, the empty set belongs to this domino poset and is a minimal element. So Q minus P even, because there are several one element subsets. So then formally what we have, even before we have any triangulated structure, we have a representation of this poset by functors, by units or counits. So adjoints give representations of this poset under either inclusion or by the opposite inclusion. So this will be by units. This is by coordinates. So, but if we have a triangulated structure and sort of we gloss over the question how we make how compatible are all those maps and the complexes, we simply assume that everything is DG enhanced, and we take the total object of this. So every value, which we can simply imagine that every value of every functor like this is a complex, and on every object we have something like a double complex, and we take the total thing. So let me introduce some notation. Maybe I'll just keep this one for the future. Let's call TPQ of F is the total factor of annotation. I forgot it was CPQ. CPQ and TPQ with this direction. It's the total factor of this one. So there are either end functors or functors from D to D, or functors from E to E. From D to E, or the functors from E to D, depending on the parities. So either D to D, or D to E, or e to d, or e to d. There's some kind of 2x2 matrix floating around here, which I'll explain later. It's kind of convenient to think of this in terms of such matrices. So, and then I first want to formulate this definition, seemingly not so motivated. Then I'm saying that a functor is n-spherical if the complexes of appropriate length represent either equivalence in the case when they are end-of functors, or represent 0 when they are cross functors.
I have a question.
Yes.
What examples should we have in mind?
I have examples related to periodic orthogonal decompositions, and I'll discuss later. So,
Okay.
yes.
I have another question.
Yes.
So if I have a category and a spherical, I have ordinary spherical functors, and I take the tensor product.
The tensor product, I don't quite understand what is meant by that. Maybe.
Okay.
No, but I'll give an example. I'll finish with an example, so which will be very, very understandable.
Okay.
Yes, there will be an example. Yes. So let's hold this part. So I just give this seemingly unmotivated definition. So F is called n-spherical. N-spherical if this one corresponds T upper star with respect to 0 to n minus 2 of F from D to D is an equivalence, and the previous, this one 0 to n minus 1 of F, which looks longer but actually is the same length with respect to the length of the complex from E to E is quasi-normal to 0. And so there are other versions when the order of those are reversed.
Sorry, there's a small n and a capital N.
Oh, that is a mistake, yes. Yes, so the small n should be equal to the
Okay.
Yes, I apologize.
So there is no condition on the smaller values, it's just on this.
For this one, yes. It's not up to this, it's for this way, yes. Okay, so now I want to explain somehow the motivation for this, for this definition, how it appeared, and what does it describe. Let me call this part relation to periodic orthogonals. So I recall that the concept of a semi-orthogonal decomposition of a triangulated category. So I have a triangulated category C, and the notation is like this, E and D. So there are two triangulated subcategories for which home from this notation from E to D equals 0. So D equals to the right orthogonal of E, so that consists of all objects for which this is true. That it is 0. E equals the left orthogonal of D, and every object, every C fits into E, C, D, in the exact triangle. So in this case, we say that if we have this pair is determined by any of those two categories, because the other one is the orthogonal, and the category E is called, if I'm correct, so D is called left admissible, E is called right admissible. So D called left admissible, left admissible, and E is called right admissible. But now we can say, we may ask if something is both left admissible and right admissible. Or we can say that something has orthogonal, and this orthogonal is admissible, and the next orthogonal is admissible. So suppose we can go forever. Suppose suppose T is, let's say, infinitely admissible. Now clashes with modern terminology. It has nothing to do with infinity categories. it just means that we have D. We can write D orthogonal, which will be E, but that will be a second orthogonal, or the third orthogonal. So left orthogonal, and each pair. So let's call it D second. Let's call it D third. So and then for every K in Z, we say that C is a semi-orthogonal decomposition formed by dk and dk plus 1.
Is there an example for that?
Huh?
Is there some motivating example for that?
Yes. So if I'll probably get to the example later. But I already sort of removed a little this question to something else, and then I'll remove this question to something else, and then. So maybe let me make a picture. Also, I would need to say that the kth orthogonal is identified with the k plus second orthogonal by the mutation. It is something like this. Suppose we start with D. Suppose this is D. This is D left orthogonal, and this is D right orthogonal. Then there is a canonical identification from here to here called the mutation. Which means that since those two form sort of a basis, we take this object, we decompose it in this basis, and take this projection, and take this part of this decomposition. And this is going to be an equivalence. This is the mutation. Now, in such situation, a way of forming semi-orthogonal decomposition is by so-called gluing functor. Was discussed by Bondal and Kuznetsov and Lutz and others. So suppose we start with the functor f from D to E, from D to E. Then it's a functor, what I'm saying. So in this case, for this semi-orthogonal decomposition is a functor such that home in C from object D to object E equals home in E, home in E between f of D and E. So, or put differently, we have this orthogonality in one direction, but in the other direction there is home, there is a pairing. So, and we realize this pairing in terms of this functor. So, and if it is given as a DG functor, so it's a DG functor, from this we can recover. So can recover C explicitly. And a good notation which I want to use, I write S1 of F, signifying the first terms of the Waldhausen S construction. Waldhausen. So basically, in elementary terms, it says that an object of the new category, so object, it will be data So it's data of convexity of object D and object E, and morphism of gamma from E to f of D will be closed degree 0 morphism. So if you sort of make such things into a DG category, then the corresponding triangulated category will have this type of semi-orthogonal decomposition. So now the relation of this with the adjoints is kind of clear, because since in this chain of orthogonals, they are identified with the interval 2. So we can write corresponding gluing functors for the orthogonals, and then would be the adjoints of the original functor. So it is kind of known and easy. So if f is a gluing functor for the composition of E and D, then for the decomposition D double orthogonal and E, the gluing functor is the adjoint. Is f adjoint, which means that if you identify this with D, you identify this in D by mutation, then the corresponding functor is the adjoint. For the other one, it is the other adjoint. So we can say that here, this gives f, this gives f adjoint, this gives f left adjoint, and so on. So now I want to formulate a sort of elementary, if you want, theorem that those complexes, the complexes of adjoints, they describe the matrix elements of the identity functor in this with respect to two different decompositions. That's probably the theorem of my talk. So consider two semi-orthogonal decompositions. Suppose C forms by E and D, and C equals, again, there are different versions for, this is one version. Suppose we have E left orthogonal of size 2n, and D left orthogonal of length 2n. Now this is again identified with E, and this is again identified with D. Then the matrix elements, so to say, of identity functor of C with respect to those semi-orthogonal decompositions, which means we take an object from here and we decompose it into parts and call the corresponding things the matrix elements. So with respect to this R, so maybe I write it here. So I write so suppose it's D, E, D, and E. So basically this will be those total complexes of adjoints. So rather, sorry. Let me just say it this way. This would be T minus 2m plus 1 minus 1. Here it will be T minus 2m plus 4 minus 2. I may screw this up a little. So it will be T something. Will be, and this will be clear what it is just from the explanation. So those two will be those which are required to be equivalences. So there will be the end of functors. So those that in the definition of a spherical and spherical functors are required to be equivalents. Yeah. And those two, those that are required to be zero. Zero in the definition of n-spherical functor.
I'm sorry. So these total complexes are total complexes for the
functor f.
Where is the functor f?
I say suppose we have a semi-orthogonal decomposition with the functor f.
Oh, f is the Bloom functor.
Yes, suppose f is the Bloom functor for ED. So basically to give a functor is more or less the same as to give a semi-orthogonal decomposition.
So these second two n-orthogonals, these are subcategories, they're equal, but they're isomorphic to your...
Yes, they are canonically identified. So, and if you write sort of the matrix elements of the identity functors, we get a matrix, a 2 by 2 matrix of functors. 2 of them will be end of functors, and 2 of them will be cross functors. So then the corollary is that an n-spherical functor describes situation. If f is an n-spherical functor, then the chain of orthogonals closes with the period 2n. Yes. So corollary. What time is it? Okay, it's not so bad. So f is n-spherical if and only if d orthogonal to n equals d, and e orthogonal to n equals e. So the chain of orthogonals will be periodic with period to n. To n periodic. This generalizes the known property of usual spherical functors that orthogonals are 4 periodic, and this is a theorem of Halpern-Lanster and Shipman. So for n equals 2, we get usual spherical functors. So the orthogonal is 4 periodic. Halpern-Lanster. So, and in this situation, so when we have such a composition of orthogonals, then we have sort of the composition of mutations. Suppose this is the second orthogonal, then the fourth orthogonal, then the sixth orthogonal. If it closes, then the composition of mutations gives me an end of functor, which is an equivalence. And this composition of mutations would be the corresponding n-spherical equivalence, albeit those which are required to be those diagonal elements. So n-spherical twist, so to say. Is the composition of mutations. Composition of mutations. Now let me consider a few examples. examples. So, example 1 would be the category of representations of an minus n plus 1 quiver. This is something that appears in combinatorial modeling of Fukaya categories all the time. So the category C would be dB of a n minus 1 mole. So it has a semi-orthogonal decomposition because it's a quiver. So it's something like this. This has semi-orthogonal decomposition into subcategories corresponding to quivers sitting at one point only.
What happened? Plus one?
Huh? Say it again?
You have both plus one and minus one.
N plus 1, not
Oh,
minus 1. Just a type.
Let me say minus 1. Yes, yes, I think it's a minus 1 because a2, yes, a minus 1.
So for the usual spherical there, would you get A2?
Huh?
For the usual spherical there, would you get A2 or A3?
For the usual, we get a1.
I
Okay, okay. So it has semi-orthogonal decomposition of several copies of the category dB of x.
for A1, you don't really get a decomposition, right?
Yes, so let me consider this hierarchy. So first of all, there will be, so let me just write what I want to say. dB. So there will be n minus 1 times. So let me do it like this. Suppose this category is D, and everything else is E. Then it's rather easy to see that the orthogonals will be periodic. Then D orthogonal to N will be equivalent to D, which means that the corresponding gluing functor, which will send dB vector to the category of representation of n minus 2 quiver, dB of a n minus 2, the functor would take a vector space V to a quiver V 0, 0, 0 would be N-spherical.
Excuse me, so it does mean that if you have an equivalence grammatically for spherical or free spherical?
What?
If you have an equivalence,
What?
okay, so this is like free spherical.
Spherical, I think it is like previous level, it's one spherical. I think equivalence is,
Okay, if n is equal to 3 in this picture.
if
And
n,
the functor is an equivalence.
if n equals to 3, then n minus 1 equals to 2, and it is two spherical, which means it is spherical, yes. Yes,
Spherical in the ordinary sense.
yeah, in order.
So it seems that this is your main example, right? So maybe you explain all your sequence of adjoints and how all this looks.
But it probably will take me that quiver, but you can do everything. I'll give you another example of the sequence of adjoint at the end, and the end is near, so don't worry. So, example 2. Suppose we have another example, how can we make, so let me soup up this version a little bit. Suppose f from A to B is a usual spherical. Then we can form S, what I write, Sn of f is the nth Waldhausen category of f. I explain in a moment. So it's objects. On data like this, we have, first of all, n objects of B, n objects of B, and then a morphism from the last one to f of A. F of A. So n objects of B and a diagram like this. It has semi-orthogonal decomposition, like this, B, 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 A. And let me call this D, and let me call this E. So of course this can be done for any functor, but if f is spherical, that this is a periodic, so has to n periodic orthogonal, and there are similar functor there, which is n-spherical, has to n periodic orthogonals. So now, if you want to write a sequence of adjoints, so that the easiest context would be that of a projective variety, functors between projective varieties. So let's try to consider the analog of a concept of a spherical object. So example 3 would be like this. Suppose D is just a derived category of vector spaces. And E would be the derived category of a smooth projective variety. So smooth projective. And the mesh. So the factor F, which just sends the field K to an object. So it's tensoring with an object E. F organizes something, tensor E. Then in this case, it's indeed easy to write all the adjoints. The adjoint in this direction would be F. Right adjoint, it would be home from E to something. Now, the next adjoint, the second adjoint in this case, F, double adjoint, it would be something, but here would be E tensor the dualizing sheaf. It would be tensoring with E tensoring omega of n, omega x of n. And F triple adjoint, it would be home from this one to something. And so on. So then will be then this thing will be squared and so on. So we call so it's natural to say that E is an n-spherical object if this factor is an n-spherical factor. Call E an n-spherical object. If F is an n-spherical factor. Now so an ordinary spherical object will be n-spherical for n equals 2 and only for n equals 2. So let me write an example of this complex of factors. Let me spell this out in that example. So for n equals 3.
Can you say what the self-x of an n-spherical object is?
What?
The self-x of an n-spherical object?
Self-x?
I mean, the endomorphism algebra.
In which sense it's an
No, I don't know yet. So let me. It's. Yes, I probably can say it is the same as for the real projective space. So for three spherical objects, it will be the same as for RPM. But let me not discuss it. So for n equals 3, this complex would be like this. Would be n of functors. For n equals 3 would be n of complex of n of functors of this category, which may be a complex of DG vector spaces. DB vector of DG spaces. The functors are given by tensoring these DG spaces. So it would go like this. Would be K. This it would go to home EE. I denote this algebra A. This actually refers to the equation. That would be home home from E tensor omega of n. E, and again would be home from E to E, be 1, 0, 1, and this would be A tensor A. So A would be this algebra of endomorphism of n-spherical object. So we want this to be an equivalence, which means this complex should have total homology of degree 1. So should have so home means at home. So homology, total cohomology of dimension 1, dimension equals 1. Homology in only 1 degree, and in that degree it should be equal to 1. So that tensoring with this DG space would be an equivalence of categories. So the most interesting map is here. Maybe I won't say what it is. It's easy to figure out from the duality. And a good example in which it is really so, and this sort of explains the point of view on n-spherical functors as real projective spaces and more general length spaces, would be like this. So example would be example. Suppose X is an Enriquez surface. So then m equals 2, the dimension equals 2, what am I saying? Omega squared equals 4x, and omega equals to omega inverse. So here we have home from something to E, which means we have omega inverse. But on an Enriquez surface, omega would be the same as omega inverse. So the complex will be like this. K would be goes to K, goes to K, and here would be K of minus 4, would be K. 1, 1, 1, 1, something. And cohomology would be one dimension. H dot is one dimension. So then we should say that in this case it is approximately an RP2 factor. RP2 factor. So since an Enriquez surface is the general, so if we think of Calabi-Yau varieties as generalization as complex analogs of spheres, then an Enriquez surface is a complex analog of RP2.
You mean RP2 object? You're looking for an RP2 object of the
Well, yes, but to say, if we say that it is not a well-defined a priori concept, doesn't quite make sense. What is an RP2 object? Because the homology of RP2 with complex coefficients, you don't see anything. And the endomorphism algebra A is simply R gamma of XO. In this case, it's K. It's the same as a real homology of an Enriquez surface. So we don't see anything. So
how do you see this in the same orthogonal decomposition?
Oh, no, the semi-orthogonal decomposition would be this plus the category of vector spaces.
So this whole story is characteristic zero.
The whole story, yes, I imagine, yes. I don't know much about Enriquez surfaces with positive characteristic.
No,
so things may go screwy here in characteristic too. Yeah.
So this, you have this n-dimensional.
We can do higher dimensional versions of this, yes. So maybe let me finish by just doing the sort of conceptual meaning that so n-spherical functor. Another, a better name for this, something like length space factor. Length space. So length space something like a sphere as of some dimension, modular ZP. So this n would be mod z n minus 1. Yes, it would be something like this. Of course, naively, it is confusing because if you only look on the algebra of endomorphism, you don't see it. But this is sort of seems to be a reasonable way of looking at such examples.
Say it again?
Say it again?
What's the characteristic you could see?
Yes.
You won't get.
Yes, yes. But I'm even less sure of what I'm saying in positive characteristics, so I'd rather not say it.
Forget the brief, just for,
Huh?
just for an example already.
For an example, it's okay, of course. Yeah. An example can be any characteristic. Yeah. Thank you very much.
Questions?
So what's the CPN functor in this language?
No, CPN is other people know better about this, and you know who. But
But it doesn't fit in this picture.
it doesn't fit in this picture, no.
That's what-
No.
But can you just explain this, because I didn't understand the mnemonic. How did you, from this diagram, how did you get RP2? What's that?
From this diagram, we don't quite get RP2. I'm just saying that if you want to come with a metaphorical name, the word should be the metaphorical name. If the example,
Why?
well, because if K3 surface is a complex sphere, yeah, because it's a complex orientation, yes, then the surface is a complex RP2. So if you take a skeleton, for instance, right, or a set of, sometimes maybe the real locus of, if you degenerate an Enriquez surface into union of projective planes, then the skeleton of degeneration, the graph or the simplicial complex has chances to look like RP2.
So what was this, that there is one more object in there, this...
Say it again?
So you were saying that if you add one more object to this...
No, I'm saying that when we interpret a functor, properties of functor in terms of orthogonals, then orthogonals where? In the category which is glued out of the source and target of the functor. So here, the functor would be from the category of vector spaces to the category of coherent sheets. So given by the tensoring with an object. So out of this, we should glue a new category. So and periodicity of orthogonals will be in that category.
So this is a subcategory of the category of the N-space?
No, it's an over category.
Questions?
So this example is in Postman generalizes to find root stacks. If you take school divisor, you take some nth root stack.
Yes, I think so. Yes.
Okay, any last questions? Okay, if not, let's think we should.